All right, welcome to the deep dive. Today we're going deep into some really cool stuff in artificial intelligence.
Yeah.
We're looking at
This is the good one.
it's called switch transformers.
Mm.
And this is all about language models.
Yeah.
You shared a really great research paper with me.
Yes.
And what we want to try to do today is extract
Hmm.
some of the core ideas, the real fascinating aha moments from this,
Absolutely.
and try to convey them in a way
Yeah.
that hopefully is memorable and understandable for everyone.
Yeah, it's a very dense paper.
Yes, it
There's
is.
a lot in there.
It is. And
It's very exciting stuff.
it is. It is. So
Yeah.
so let's just jump right in. What is the core problem that that switch transformers are designed to solve?
Well, when you think about traditional deep learning models, they use the same parameters
Mm-hmm.
for every single input that they get, right? It's
Yeah.
like this big brain that's
Yeah.
processing everything the same way. And as we try to scale these models up
Mm.
to be able to handle more complex tasks, more data, this approach starts to run into problems.
Yeah, because you can only make the brain so big before it gets too
Exactly. You hit computational limits.
right.
It becomes too expensive to train.
It's too slow.
Yeah, too slow.
Yeah. Okay.
Too much memory, all these things.
So instead of making the brain bigger, we're doing what?
Well, switch transformers propose something really interesting.
Okay.
Instead of having one giant set of parameters, they have multiple sets.
Okay.
And we can think of these as like experts,
Okay.
right? And so for every input that comes in,
Mm-hmm.
the model decides, okay, which expert is best suited to process this particular input.
So it's like a triage.
Yeah,
Like
right.
when you go into a hospital,
Exactly. Like you go to the hospital.
you don't see every single doctor.
Right. You don't go to the cardiologist if you have a broken arm.
Right. Yeah. You go to the
You go to the expert for your particular problem.
specialist.
Right.
So for our listener out there,
Yeah.
this is a really great episode to listen to if you are, let's say, prepping for a meeting about AI advancements.
Absolutely.
If you are trying to understand the latest in natural language processing,
Yep.
or if you're just curious about how these truly massive AI models can work
Yeah.
without needing like racks and racks and racks of computers
Exactly.
for every single task that they do.
That's the really cool thing.
So,
Yeah.
so what is our source material for today's deep dive?
Our main guide for this journey is a research paper
Okay.
called Switch Transformers, Scaling to Trillion Parameter Models with Simple and Efficient Sparsity.
Okay.
It's by Fetus, Zoth, and Shazir.
Okay, great. And
Yeah.
that paper really lays out a lot of the fundamental concepts.
Yeah.
And
does.
and it does a great job of explaining this.
Mm-hmm.
So they talk about this concept called a mixture of experts, or MOE. What is the basic idea behind that? And what were some of the roadblocks that kept it from becoming widely used?
So the idea behind MOE is kind of what we've been talking about, right? Instead
Right.
of one big neural network, you have a collection of smaller networks that are more specialized.
Okay.
These are the experts.
Okay.
And you have a mechanism called a router
Hmm.
that decides for each input
Okay.
which expert, or sometimes multiple experts, should process this.
Okay.
And then the results from those experts are combined to produce the final output.
So why didn't it just,
Yeah, that's a good question, right?
take over the world?
It seems like a good idea.
Yeah.
It seems very intuitive.
Right.
But there were some challenges that made it hard to use widely.
Right.
One was complexity.
Okay.
Building a system with lots of expert networks
Okay.
and a routing mechanism is, well, it's just more complex than a single model.
Yeah, right. Yeah.
So that was one challenge.
Okay.
Another was communication. When you're training these models across many different computers,
Mm-hmm.
the data has to be sent back and forth between the experts.
Okay.
This can be a bottleneck,
Yeah.
that can slow things down.
Okay.
And then the last challenge was training stability.
Okay.
These MOE models were often kind of finicky,
Gotcha.
hard to get them to train consistently well.
Right.
And so, yeah, but the paper mentions that these factors really limited the adoption of this approach.
So how did switch transformers come in and save the day? What was their big innovation?
The key innovation was actually simplification.
Okay.
They took this idea of routing, right?
Yeah.
And instead of sending each input to potentially multiple experts,
Okay.
they said, no, we're only going to send each input to one expert.
Wow.
And this is called K1 routing.
Okay, just one. So that sounds almost too simple, right?
It does. But this simplification has some really big advantages.
Okay.
Like 3 main advantages.
Okay, let's hear them.
First, it reduces the computation that the router needs to do
Okay.
because it only has to pick one expert, right?
Makes sense, yeah.
It doesn't have to do all these complex calculations to figure out how to combine multiple experts.
Gotcha.
Second, because each input is only going to one expert, the capacity that each expert needs can be potentially cut in half.
Oh, okay, that makes sense.
Compared to a system where an input might go to multiple experts.
Right, okay.
And the third advantage is that it simplifies the whole routing process, which leads to lower communication costs.
Gotcha.
You're not sending as much data back and forth between different parts of the model.
So it's kind of like, instead of having to have a committee meeting with all the experts,
Exactly.
I'll just have like one expert come in and...
Yeah, you find the right expert.
Yeah, and give you the answer, right?
Exactly.
Okay, cool.
You know,
So
yeah.
this routing, this efficient sparse routing,
Yes.
how does that actually work behind the scenes?
All right, so they use this technology called Mesh TensorFlow, or MTF.
Sure. Okay.
And this is what allows them to train these massive models across lots of different processors.
Okay.
Like, think of it as a way to organize the computation
Gotcha.
across a whole bunch of powerful computers.
Okay.
So they can visualize their computing infrastructure as this, like, grid processing unit.
Oh, right.
And they can split up the model and the data across this grid.
Okay.
So it makes it much easier to scale up the training to these huge numbers of processors,
Okay.
like TPUs, which are specialized hardware for machine learning.
Right. Okay.
And one thing about MTF
Yeah.
is that it requires knowing the size and shape of all the data
Okay.
beforehand, like before you start training.
Okay.
It needs to know how much data it's going to be working with.
So they need to kind of plan out the whole thing in advance.
Yeah, exactly.
Interesting. So
Yeah.
how do they determine how much work each of these experts can handle?
That's a good question.
And what is this capacity factor that they mentioned?
So each expert has a certain processing capacity, right, which is the number of inputs that it can handle at once.
Okay.
And this is determined before training.
Okay.
And the way they calculate it is they take the total number of inputs in a batch, divide that by the number of experts,
Okay.
and then they multiply by this thing called the capacity factor.
Okay.
And the capacity factor is basically a bit of extra space,
Okay.
right? Because the routing of inputs to experts isn't always perfectly balanced.
Right.
Some experts might get a few more inputs than others.
Gotcha.
So the capacity factor is like a buffer to
Okay.
make sure that no inputs get dropped.
Okay. So it's kind of like
Yeah.
like if you have a restaurant
Yeah.
and you're seating people at tables,
Mhm.
you might want to have a couple of extra tables.
Exactly.
Just in case a big party shows up.
Exactly. You don't want to turn people away.
Right, right. So is there a trade-off with this capacity factor?
Yeah, there is.
Okay.
If the capacity factor is too large,
Okay.
you might have some experts sitting around doing nothing
Oh, okay.
because they have all this extra capacity.
Right.
But if it's too small, then you risk dropping inputs.
Gotcha.
So it's a balancing act.
Okay.
The paper mentions that they usually had very low drop rates in their experiments,
Okay.
like less than 1%.
Okay. So they found a happy medium there.
Yeah, they did.
Okay. So they also talk about this this thing called the differentiable load balancing loss.
Mm-hmm.
And that sounds, I don't even know what that means, but it sounds important.
Yeah, it is important.
What is it?
So the goal of this loss function is to make sure the work is spread evenly across all the experts.
Okay.
Right. You don't want some experts being overworked
Right.
while others are just, chilling.
Yeah, yeah.
And the way it works is it looks at the fraction of inputs that each expert is actually getting
Okay.
and compares that to the fraction of routing probability that's assigned to each expert.
Okay.
So basically it's saying, we want the experts that the router thinks should be busy to actually be busy.
Okay.
And we want to make sure that the router isn't just favoring a small group of experts all the time.
Gotcha.
So it encourages this even distribution of work.
Okay. So they mention a specific value for a parameter in this loss function.
They do.
It's usually around like 10(2) or something like that.
Right.
What's the significance of that particular value?
So that's a scaling factor that controls how much importance the model gives to this load balancing
Okay.
versus its actual task, which is learning language.
Right.
And they found through experimentation that this value
Okay.
was a good balance.
Okay.
It was large enough to promote even load distribution,
Mm-hmm.
but not so large that it overwhelmed the main goal of the model.
Gotcha.
So it's a delicate balance.
So how did the switch transformers perform? Like, what were the benchmarks? How did they do?
So they did a lot of experiments, right? They compared their switch transformer models to other well-known models, like T5, which is the text-to-text transformer.
Okay.
And they compared it to both the base version and the larger version of T5.
Okay.
They also compared to the more traditional mixture of experts models.
Okay.
And the main pre-training task they used was this thing called masked language modeling.
Okay.
And they used this massive data set called the Colossal Clean-Crawled Corpus, or C4.
Okay.
And basically what masked language modeling is you give the model a sentence with some words missing.
Okay.
And you ask it to predict the missing words.
Okay.
So it's a way to test the model's understanding of language.
Gotcha. And what were their key findings from this comparison?
Okay, so they found three main things.
Okay.
One, the switch transformers outperformed both T5 and the traditional MOE models on a speed quality basis.
Yeah.
So for a given amount of computing power and time, the switch transformers got the best results in terms of language understanding. Second, they found that the switch transformer architecture had a smaller computational footprint than the traditional MOE approach.
Yeah.
So even when they scaled up the switch transformer to match the training speed of the MOE model, it still performed better on a per-step basis.
Okay.
So it was more efficient.
Gotcha.
And third, they observed that switch transformers performed well even with low expert capacity factors.
Okay.
Which is important for scaling to even larger models.
Right.
Where memory constraints are a big challenge.
Right. Okay, so that's really encouraging.
Yeah, it is.
So what about scaling? How did these models, how did they perform as they increased in size?
Yeah, scaling is where things get really exciting.
Okay.
So they looked at scaling in two ways.
Okay.
First, what they called step-basis scaling.
Okay.
Where they increase the number of experts and therefore the total parameters of the model.
Okay.
But they keep the amount of computation per token roughly the same. And what they saw was more parameters led to faster training.
Wow, okay.
And better sample efficiency.
Okay.
So the model was learning more effectively from the same amount of data.
That's amazing. So more experts equals more efficient use of the data.
Exactly. It's like having more specialized knowledge.
Okay.
Allows the model to learn more quickly.
Okay. And what was the second way they looked at scaling?
Okay, the second way was time-basis scaling.
Okay.
And here, they fixed the amount of training time and the computing budget.
Okay.
So it's like saying, okay, you have this much time and this much computing power. What's the best you can do?
Right.
And they found that for the same training duration, switch transformers reached a certain level of performance much faster.
Okay, so not only are they learning faster, but they're reaching a good performance level faster as well.
Yeah, exactly.
So like double efficient.
Yeah.
It is.
Yeah.
That's awesome.
Yeah.
So building these systems, they must encounter some problems along the way.
Oh, yeah, absolutely.
So
building these massive AI systems is not a walk in the park.
No.
There are always challenges.
So they had to develop some improved training techniques for stability.
Yes.
What were some of the difficulties that they ran into?
Well, when you're training these very large, sparse models, it can be more difficult to keep the training stable compared to training a standard dense model. One of the reasons for that is this hard switching, where each input goes to only one expert. And that can sometimes cause noisy updates during training. And another factor is the use of low-precision number formats, like bfloat16, which is really good for making training efficient, but it can also make the training less stable.
Gotcha.
Especially in the routing mechanism.
Okay, so how did they make sure that the training was stable?
All right, so they came up with a few techniques. One was called selective precision training. And the idea here is that you only use the higher precision number format, float32. In the parts of the model where it's really needed, which is the router function. So they use bfloat16 for most of the calculations. But then they switched to float32 for the routing. and then they convert the results back to bfloat 16.
Gotcha.
So they get the best of both worlds.
Okay, so they're only using the more precise format when they absolutely need to?
Yeah, exactly.
Okay, that's a smart way to do it.
Yeah, it is.
What else did they do?
So they also found that using a smaller parameter initialization was helpful.
Okay.
So basically, they just reduced the initial values of the parameters by a factor of 10.
Okay.
And this really improved the quality of the trained models.
Okay.
And made the training more stable,
okay,
especially at the beginning.
Gotcha.
So it's a small change, but it had a big impact.
Okay. And what about when you take these pre-trained models and you fine-tune them for specific tasks?
Right.
Did they encounter any challenges there?
Yes, they did.
Okay.
So because switch transformers have so many parameters, right, they have all these experts,
right,
they can sometimes overfit on smaller tasks where there isn't as much data.
Gotcha.
So to address this, they came up with this technique called expert dropout.
Okay, what's that?
So during fine-tuning, they basically just increase the dropout rate in the expert layers.
Okay.
So they're basically randomly turning off some of the experts during training.
Right.
And this helps to prevent overfitting.
Gotcha.
Because it forces the model to learn more general representations.
Okay, so it's like you're giving the model a little bit of amnesia.
Exactly.
Just to keep it from remembering too much of the specific details.
You don't want it to memorize the training data.
Right, right.
You want it to learn the underlying patterns.
Exactly. Okay. So how did these fine-tuned models actually perform on real-world language understanding tasks?
So they tested them on a whole bunch of different benchmarks.
Okay.
Like GLUE and super GLUE, which are standard benchmarks for language understanding.
Okay.
They also tested them on summarization tasks.
Okay.
Like CNN Daily Mail and XM, question answering tasks like Squad, and a bunch of other tasks that test reasoning and knowledge.
Okay.
And they saw some really good results, especially in super GOE.
Okay.
They get big improvements there.
Okay.
And they also got good results on things like common sense reasoning, factual knowledge, and summarization.
Okay.
The only place where they didn't see improvements was on this one benchmark called ARC, which is the AI2 Reasoning Challenge.
Gotcha.
But overall, the results showed that the switch transformers were really good at transferring their knowledge to new tasks.
Okay.
So they were learning generalizable representations of language.
Okay, so that's really encouraging.
It is, it is.
So deploying these massive models sounds like a huge challenge.
Yeah, it's not easy.
So they must have explored some ways to make these things more practical.
For
the real world, right?
Yes. So they looked at this technique called model distillation.
Okay.
And the idea here is to take the knowledge that's learned by the big model and compress it into a smaller model that's easier to deploy.
Gotcha.
So it's like, you have a really smart teacher.
Right.
And you want to teach a student everything they know.
Right. But the student has a smaller brain.
Exactly. The student has a smaller brain.
Yeah.
But they can still learn a lot.
Yeah. Okay. So how did they go about doing this teaching process?
Well, they tried a couple things.
Okay.
One was to initialize the smaller model with the weights from the non-expert layers of the bigger model.
Okay.
And they also used this special training process where the smaller model tried to not just predict the correct answer, but also to mimic the predictions of the bigger model.
Oh, okay.
So it's like learning from the teacher's thought process.
Yeah, yeah. It's like not just learning what the answer is, but learning how the teacher arrived at the answer.
Yeah, exactly.
Okay, cool. Yeah. So how much of the performance were they able to retain with this technique?
So they were able to retain about 30% of the performance gains.
Wow. 30%. That's pretty good.
Yeah.
For shrinking it down that much.
Yeah, it is.
Okay, what about multilingual capabilities?
Yeah, so they also looked at that.
Okay.
They trained a model called MSwitchBase on a data set with text from 101 different languages.
Wow, okay.
And they compared it to MT5Base,
okay,
which is the multilingual version of T5.
Okay.
And they found that MSwitchBase was better at understanding all 101 languages.
Wow, all of them. Okay, that's amazing.
Yeah, and it was about 5 times faster than MT5Base.
So switch transformers, good for a lot of languages.
Yeah, seems like it.
Okay, cool. So how do they actually build these truly enormous models? Like what are these data model and expert parallelism techniques that they talk about?
Right. So these are ways of distributing the work of training these models
Okay.
across many different computers.
Right.
So data parallelism is a common approach
Okay.
where you give each computer a different subset of the data,
Okay.
but they all have a copy of the whole model.
Okay.
And model parallelism is used when the model itself is too big
Okay.
to fit on one computer.
Okay.
So you split up the model across different computers.
Gotcha.
And then expert parallelism
Okay.
is specific to switch transformers.
Okay.
And it means that each computer is responsible for a different set of experts.
Okay.
So you're splitting up the experts across the different computers.
Gotcha.
And then the router has to figure out how to send the data to the right experts.
Right. Okay. So they mentioned these two, like, really, really big models. They do.
Switch C and Switch XXL.
Right. Yeah.
How big were these things?
So Switch C was 1.6 trillion parameters.
Wow.
And Switch XXL was 395 billion parameters.
Okay, so those are some serious, serious models.
Yeah, they're huge.
Yeah. And how did they perform compared to the existing T5 XXL?
So in terms of pre-training,
Okay.
both Switch models were better than T5XXL. They achieved a lower perplexity,
Right.
which means they were better at predicting the next word in a sequence.
Gotcha.
And Switch C was about 4 times faster
Wow.
than T5XXL.
That's incredible.
Yeah, it is.
So even at that scale, it's still faster and better.
Yeah, and interestingly, they observed some instability with Switch XXL during training,
Okay.
but Switch C was stable the whole time.
Huh. Okay, so even though XXL was faster, it was a little bit less stable?
It was.
Okay, what about fine-tuning?
Yeah, so they did some fine-tuning with Switch XXL.
Even though it wasn't fully trained yet?
Okay.
And they got some really good results.
Okay.
Especially on knowledge-based tasks.
Okay.
Like question answering.
Okay.
It was better than T5XXL on those.
Okay.
But they noticed that the gains from pre-training didn't always translate perfectly to tasks that required more complex reasoning.
Okay.
So that's something that needs more research to figure out how to really leverage those massive models for all kinds of tasks.
Okay, so before we wrap up here, what are some of the key takeaways from this paper?
Okay, well, the paper highlights some really interesting things.
Okay.
One is that more parameters are good.
Okay.
Even if you keep the computation per input the same.
Okay.
So just having more parameters in your model can actually improve performance.
That's counterintuitive.
Yeah, it is big.
Yeah.
They also found that switch transformers work well even with a small number of experts.
Okay.
So you don't need like thousands of experts to get benefits. And another important point is that sparse models, like switch transformers, are just better than dense models on a speed accuracy basis.
Okay.
They're more efficient.
Gotcha.
And they get better results.
Okay.
They also showed that you can compress these big models using distillation, which is really important for making them practical.
Right.
And finally, they found that switch transformers can be more efficient than model parallel dense models when it comes to training time.
Okay.
So they're faster at reaching a certain level of performance.
Gotcha. Okay.
Yeah.
So what about the future? What are some of the directions that they see this research going in?
Yeah, so they talk about a bunch of interesting directions.
Okay.
One is improving the training stability of these really big models.
Okay.
They want to make sure that these models can be trained reliably without any issues.
Gotcha.
They also want to understand better how pre-training quality and computation per token and number of parameters all affect downstream performance.
Right, okay.
They want to know how to best balance all those factors.
Right.
And they're also interested in exploring different ways of combining parallelism strategies.
Okay.
Like data model and expert parallelism.
Right, right.
And they also want to look at using different kinds of experts.
Okay.
Like heterogeneous experts.
What does that mean?
So that means that the experts could have different architectures.
Oh, okay.
Or different capacities.
Okay.
So it's like having a team of experts.